Okay, hello everybody. Thank you for coming along. Thank you for staying. I know it's Saturday afternoon. It's time to go and have some more beers. Do you want to introduce us? Sorry, that's your job, isn't it?
No, it's cool. You can just have fun with the panel. I think you got it.
Okay, cool. Thank you. The panel is called. Let me find. We have a name for it. A new root of trust: changing computing with trusted execution environments. Okay, and with me I have, first of all, my name's Mike Bassal. I'm the Executive Director of the Confidential Computing Consortium, which is a Linux Foundation project, which is basically the industry body for confidential computing and trusted execution environments. And with me I have Nathaniel. Nathaniel, do you want to introduce yourself? Say what you do.
Hello, everyone. Can you hear me? Yeah, here we go. My name is Nathaniel McCullum. I'm a principal software architect at ARM, and I've been working in confidential computing basically since the beginning, so quite a long time.
And Fahima.
Yes, my name is Fahima Rezai, and I'm an offensive security researcher at Intel. I have been working confidential computing only 4 years, not forever. But yeah, well, our team actually mainly does offensive security research and reviews on the confidential computing technologies at Intel in terms of architecture and code, source code.
Okay, so let's start off with some basic definitions. We've had a number of things about TPMs here, and TEs are not TPMs. So, Nathaniel, why don't you just tell us very briefly what a TE is?
Sure. So a TPM is a bundle of services. It does like state management for keys. It does attestation of the actual hardware and the firmware that's running on it itself. It can do various cryptographic operations. But the actual applications that use the TPM are running unencrypted, in a virtual machine or even on bare metal hardware. And they can use the TPM to do various things. So one of the key things that's very relevant from TPMs to the question of confidential computing is the question of attestation. In the TPM world, this is often called measured boot, something to that effect. And this is the thing that sort of starts with a cryptographic root of trust and allows you to build up every software layer above that. And confidential computing definitely uses that technology, but it doesn't use a TPM chip. It uses something that's built into the CPU itself.
What GPU?
And it's combined with a second security principle, a new security barrier, which is the confidential computing barrier, which is that you can basically create a mode for doing processing. This is most often a virtual machine, and you can actually encrypt the memory of that while it's running. So the actual application, while it's running, still maintains its full cryptographic envelope of the entire application. It can't be tampered with by the host or by another malicious process on the system. And when you combine that with the root of trust, you get a very powerful combination. So that's the main difference.
Okay, so it's chip level instructions, right? Do you want to go into that a bit, Fahima?
Yeah, actually, I just want to add two things here. One is that, TEE actually is isolated from the main CPU. However, TPM is a standalone chip that is interfaced to the rest of the system. The other thing is the application and the security services that provided by each technology. So TPM actually provides the integrity and confidentiality to the cryptographic keys. However, I think TEE provides the confidentiality and integrity to the data and application, the code that actually is running in that enclave. So
one way to think of it is that basically a TE, you ask the CPU to provide you with a bunch of memory pages, and it encrypts those memory pages in such a way that even if you have kernel access, hypervisor access, admin access, you can't get in. So let's say you want to be running a web server in the cloud, and you have an HTTPS web server. It needs a private key. In the standard case, the CSP, Microsoft or Google or whoever it may be, could look into that private key and do anything they want with it. If you set up a TE correctly, they cannot do that. So you're isolating yourself from the rest of the host. And that is one of the key things that it allows you to do. And I just should briefly mention that these capabilities are available right now from a number of vendors. Intel has a number of technologies, SGX, TDX, TDX Connect.
Yes.
ARM has ARM9 CCA realms. AMD has AMD SEV SNP. NVIDIA has at least one, if not two, in their GPUs. And there's also some technologies coming from RISC-V as well. So one of the things that I want to talk a bit about, and I'm going to get Fahima to answer this one first, is what is this, what is attestation? What does it do? How does it work? Because it's absolutely key, right, to what we're talking about.
So attestation actually is somehow authenticating the TEE environment and making sure that you are actually running your data and application on an environment where it is genuine from the technology provider, and also it's in a good state to run your data and application inside that TEE. So that's mainly the attestation. And when we talk about hardware-based attestation, it comes from the report is actually measurement report actually is signed from using the hardware key and actually attested from the lower layer. So.
Do you want to add to that, Nathaniel?
Sure. So in computing, we basically have three supply chains. We have a hardware supply chain, we have a firmware supply chain, and we have a software supply chain. And each of those, essentially, in order to do the attestation, which is the validation that a computation that I'm about to hand my personal data to, right, is the computation that I actually expect it to be, and that it can't be modified after I hand the data out, right? That's the important thing. So if I'm about to give you my social security number, I want to know exactly what you're going to do. It's 111-11-1111.
Oh, nice.
Yeah, thank you. So I'm about to hand over my social security number, right? And I want to make sure that the code on the other end is going to do only what it claims it will do with that code, and that it can't be modified after the fact to do something different. So those three supply chains are the way that we get those properties. And the supply chains, of course, they have to be endorsed by someone, meaning someone says, this is the thing that I built with these technologies. And then the attestation basically is downstream of that, and it verifies the environment by taking information from endorsers and validating, yes, that this is in fact the hardware, firmware, and software I expect to be running.
Cool. So I want to give an example of this. And so the example is, I am a user of this technology. I want to be putting something in a TEE. I've got some really sensitive data and possibly a sensitive algorithm, and I want to set up one of these. And Nathaniel is Microsoft or Google or something like that, and he is going to provide me with a machine which will do this. And my friend Fahima down the end, Fahima's really important. She is an attestation service, okay? So I believe stuff that she says because I've got a good relationship with her, and all the stuff she's doing is open source, et cetera, et cetera. Okay, so I go to Nathaniel and say, Nathaniel, please can you set me up a trusted execution environment on this machine?
Here you go.
Excellent. And I then say, how can I be sure that you've set it up correctly before I put all my sensitive stuff in it? And he says,
oh, it's fine. It's cool.
And that kind of misses the point, right? As soon as we've done there, we've missed the point. So
but it's really cool. You can put your social security number in it, and I won't look. I promise.
I can't put it in because I'm not a US citizen. I don't have a social security number. But okay.
But I just gave you mine. You can put mine in.
I'm going to say I don't believe it. What I want you to do, and I want the chip to do, is to provide me an attestation measurement. So please measure these memory pages that you've just set up at my request. Will you do that?
I can't because I'm an institution, but the computer can do it.
Okay, get the computer to do it.
The computer will do it, and we'll give it to you.
Okay, thank you. I don't want it. Please send it to Fahima. Fahima, tell me about the stuff that he's just sent you.
Actually, I need to check.
Please do check.
I'm checking. Well, he's good.
Okay, so what have we just checked? And this is really important. Fahima, what did you check that he sent you?
Well, the signature and also the measurements that he sent based on the policies that we have and pre-requirements, security requirements that are there. So.
Okay, so what the chip did is it measured the memory pages took a Mac of it, obviously, and then signed it with a key which is not usable or visible for anything else. And Fahima has known good values for the stuff we're going to do. And now that she's told me it's okay, because I have a trust relationship with her, I can now deploy my stuff. So this allows me to put stuff in the cloud provider or on machines which otherwise I don't trust, and have high-level cryptographic assurance that what is running is what I believe is running and cannot be tampered or looked at by unauthorized parties. What am I missing?
So there's actually an anti-pattern in what you just described, which is that we do commonly talk about this as a tertium, right? With three different parties, where you have a first party who wants to run a computation, a second party who's going to run that computation, and a third party who will authorize that. But if you only build a system built for those three parties, then there's a variety of patterns that you can't build. But if, for example, I can give you those measurements and you can verify them directly without a verifier, a third party verifier, then you can build all other systems with that. So the simplest case is that the attestations go directly to you. You know those values from a manufacturer or whatever, and you validate them directly. Yes, there's lots of good reasons to do this as a tertium, but we do want to remember that you also could validate it yourself, which is incredibly important actually for auditing, because what happens, you look very lovely, and I'm sure that you're very trustworthy, but what happens if you're compromised, right? How do I know that the validation that she gave back to Mike is actually the correct validation? And so there's a fast path, right, where you can validate signatures. You can do this very rapidly. But what happens if Mike in the future loses trust in you? In that case, Mike needs to go look at logs, and he needs to be able to validate the attestations himself without you being involved. And so that's a very important dynamic that I want to make sure is part of the conversation.
Cool. I'm just going to pause for a moment and ask if there's any questions around this stuff right now. Oh, yeah, right at the beginning. We've got other stuff we want to talk about, but we have a question here, so let's go with that if we may.
Where do you get the known good values?
Where do we get the known good values? Great question. I'm going to let Fahima answer that, because you actually create silicon and run it. He just designs it. Well, where do you get the known good values from?
Actually, those are the hardware measurements. Actually, from the lower layers of hardware, we actually do save the good states of the hardware, and then we actually verify them by attestation.
So Nathaniel talked about endorsements, and I suspect he wants to talk about them some more.
Thanks. Yeah, so endorsements is basically how you get those known good values, right? You have to have some party that says, this is the thing that I built, and these are its values. And you have to have some mechanism to trust that. Usually that's also a cryptographic mechanism as well. But it basically all starts with a supply chain. So you start off, maybe, if you're doing some software, you start off with some source code in a compilation environment, and you produce a binary, right? That binary is the artifact that actually gets deployed. You want that binary to be signed by something, and that certificate signing hierarchy is essentially the thing that is the endorser for that particular supply chain. The verifier is the party that's going to verify that stack, right? Mm-hmm. So when the actual binary gets deployed, you want to validate not only the signature on it, like to see if you could run it, but also while it's running, you need to be able to communicate to other parties. This is what I am this piece of software. So
trust, it turns out, is really difficult, and there's some things you have to do out of band, basically, in order to allow you to build these trust relationships. And it's such a difficult thing that someone's actually written a book called Trust and Computer Systems in the Cloud, Wiley 2021. It's me. He may have a T-shirt made asking me about this, but it's very, very complex.
It says, "Have I asked you about my book?"
Yes. Have I told you about my book?
Have I told you yet? Because you're much more demanding.
Yeah, thank you. But the point is that some stuff has to occur out of band, because you need these relationships in the same way that you do with a TPM vendor to establish the initial keys and stuff like that. So we've talked about one sort of set of use cases where you're doing everything on one chip, but Fahima, that's not always the case, is it?
No, actually, at Intel we have another technology called TDX Connect, which is going to be available soon. And this technology actually provides the ability to onboard the TD-ISP devices to the trust zone. And, these TD-ISP-based devices actually will be able to communicate to the trust domain using the PCI ID link extension. So that's what we have. And actually, this is one of the use cases of confidential computing in the area of computational AI, where actually I can give an example of how the NVIDIA GPU H100 can actually interface with the TDX Connect, using TDX Connect to the TD domains, and we can interface these type of GPUs using TDX Connect.
Do you want to add anything to that, Nathaniel?
Yeah, I can just add that, we tend to think about the hardware, but just as we don't think of the software, right? Software systems are basically complex networked systems that all have distinct identities. The hardware is also that as well, right? So we actually have a network of hardware, and one of the challenges for confidential computing is not only bringing up this technology for just the CPU or for a VM, but for the entire network of discrete hardware devices. And so these are usually basically, every time you have an endorsement and an attestation of that endorsement, what you're communicating is that I've created some security boundaries, and I'm endorsing that these security boundaries will hold, right? It's a stake of your reputation on a particular set of security boundaries. And when you make that stake, that one of those boundaries might be, for example, the physical package boundary of the hardware, right? Another one might be a software boundary. Think of like, we didn't used to have separate OS processes, right? Because we had systems running in real mode. And so, when we didn't have that, right, we created this new security boundary we today call a process. Like, does that security boundary hold? Well, mostly yes, but Spectre and Meltdown and a bunch of other things, right? Sometimes they break that. And so basically what we're doing when we're creating this endorsement is we're saying that the security boundaries that I've given you as tools for you to use are going to hold, and I'm going to stake my reputational claim on it. And so that's what essentially everyone is now consuming downstream of that.
Yeah, I want to come back to boundaries in a minute, but Fahima brought up the question of confidential AI or AI using confidential computing. And I'm not entirely sure I believe in AI yet, but that's partly because I'm old. But one of I was at a major investment bank a few weeks ago, a really, possibly $1 trillion. You will have heard of it. I can't say who it was, but you will have heard of it. And they want to use AI models, right? ML, whatever you want. But they want to be building systems to make investment decisions because about, risk and stuff. And these models not only are themselves hugely proprietary and sensitive, but all of the data going into them is hugely proprietary and sensitive. They also cannot afford to run them all in-house. So they desperately want to be able to run them in the cloud, right? So they want to be able to put stuff in the cloud, and they absolutely cannot trust every single Microsoft or Google admin, or that, every Google or Amazon machine is uncompromised. They need to know that there is isolation for this model when it's running in the cloud. And so for them, being able to say, I need to set up a TE and attach a GPU with those capabilities is absolutely key, because they cannot afford to be doing stuff in-house. They want to be able to run it. And this is the sort of thing they want to do.
Actually, yeah. I would like to add something to that. Right now, we are able to actually interface the GPU and other devices with the TDs. It's not that we can't do that, but that one is I/O virtualization based on management from hypervisor. However, when we talk about TDX Connect, it's a physical link, actually, which provides the encryption from the hardware side. So that's actually faster and better. It provides better performance to the devices that connect to the TDs, because these devices can actually directly access the private memory of TDs. However, right now they can't access it. The TD needs to actually bring the data to the shared memory, encrypted and decrypted back and forth between the shared memory and the private memory. So it doesn't mean that we can't do it now. It's slow. By TDX Connect, it will be faster and better. We provide better performance.
Please, question.
The question is common. So a large investment bank running models to invest stuff can't afford to run it out. These models are not that great, right?
No, the models are great because they are big. But they can't afford to, they don't run them all the time. So you can't afford to keep machines just sitting idle to do, all the time like that. Fair question.
They're also much faster and much cheaper when you can batch the operations.
Yeah.
And so what you actually want to do is you want to collect a bunch of data if you can, right? Send it to the cloud, scale it out massively, deploy all of that, do all the inference on that or the training on that, and then shut it all back down, right? So you're not doing this on-prem.
So, someone said performance, so I'm going to ask Fahima at first. And so, presumably, this is really slow, and it's going to run twice as slowly in a TEE than it would run on its own. Or is it actually quite fast using TEEs?
Actually, in terms of performance, I don't think that we are sacrificing a lot from performance perspective. When we provide the security service that we actually have on TE and what we offer from TE, I think that's a very easy trade-off to choose TE rather than just the normal environment based on the a very little losing on performance.
Nothing. Do you want to talk about any figures?
Sure. So like early confidential compute, there was a performance penalty. In the early days, I'm not going to name any names, but one of the early implementations was pretty bad in terms of performance. It was like a 50 to 100% hit in some cases. It was AMD actually who made it really swallowable for the first time. Their first generation of SEV was like under a 3% performance hit, so that was something you could very well turn on. All modern implementations these days are now below 1% performance hit to turn on the memory encryption. So it's very, very efficient to run today, and all of the big performance losses today come from anytime you have to talk to another party, right? So if you're just doing computations, like I said, you're going to get a very minimal performance hit by turning on the memory encryption. If you, however, have to like talk to a GPU or you want to send packets over the network, you do have to have a bounce buffer for that, at least for modern software implementations. But as confidential computing enabled hardware becomes more available, you'll be able to do the direct memory I/O, and there's standards for that. For example, in the PCI group, the TDISP standard basically allows you to connect a device where that device, all of these PUs, and I'm not talking about the stink. It's the CPU, the GPU, right? Your network processors, basically all of these discrete processors, they form a network of hardware, and they're basically all going to find a way to enter a shared domain where the memory is encrypted for everybody, but they can all share that memory directly between them in a way that's encrypted. And once they can do that, basically we'll get all of our performance back, and the memory will be encrypted all the time, and we'll have cryptographic isolation between different trusted execution environments on the host. So that's the dream, I suppose.
And we'll have world peace, right?
Oh yeah, it'll also have really big wheels.
Excellent, good. And freaking lasers, I believe.
Yeah,
Excellent.
Sharks with lasers.
Yeah, sharks,
Yeah.
indeed. So, okay, so any more questions? I've got lots of. Oh, okay, fine. Let's take gentleman in the middle at the back there.
A while ago, you mentioned there were three supply chains: hardware, firmware, and software. And I don't remember if you elaborated on why firmware and software are different supply chains.
Yeah, because the firmware and software are different supply chains, because firmware is not just regular software. It seems apparently like regular software, but how firmware is actually built is a different supply chain process than regular software. Traditionally in software, you have a bunch of libraries, you can sort of combine them together on an operating system. There's a bunch of standards, everything sort of just works. With firmware, there's a lot of, behind the scenes. And so how the supply chain actually gets constructed is rather different. It also has a very, very platform-specific nature, where, by software, I'm talking about things that are essentially, platform agnostic, besides from the fact they run different instruction sets. Where firmware, again, is a very boutique supply chain. And so when I'm talking about these three supply chains, I'm trying to address the fact that in order to build this world, which I think is a much better world than the world we have now, we have to basically work with each of these discrete supply chain processes to make sure that we have something that works for each one. The development flow is just different.
Yeah. So, for instance, your application might come from Red Hat, okay, whereas your firmware might come from
Samsung or
and your actual chip come from someone else.
Yeah, but yet that firmware that comes from Samsung, right? Like, I'll talk about this in the ARM case. In the ARM case, for those that don't know, ARM's primary business model is that we design CPU IP, and then we license that IP to other manufacturers to actually go take and build. And so in our case, right, we produce reference implementations of the firmware, which the people that actually go build the chip essentially fork and create their own version of firmware from that. And so the dynamics of that supply chain are very different than just writing some Rust and using some crates from crates.io.
Okay, so another question. Let's do that.
How does it all connect? What is the best path to connect all of that to open source?
The best way to do it is have open source hardware, open source firmware, and open source software. That's easy. Next.
It's not, but like a simple example, like outside of the confidential thing, like in our case, like at some point, I'm responsible for the Linux kernel, and like at some point.
Wow, you are Linus. I didn't know. You look rather different in person.
Our kernel started crashing,
Okay.
randomly, right? And it was crashing for 6 months. We figured out where the bug was, and eventually we talked to Intel. We were using Intel. Like, oh, that looks like a bug would be hunting there. It's like, can you try this microcode? Okay. Fixed everything. It's like, okay, what was the problem? It's like, we can't tell you.
Yeah. So
How can
I can't tell you. Magic.
In all these confidential computing systems, I can't really trust the vendor.
do you want to address that, Fahima?
Well, I'm sure that all the silicon vendors and also Intel are moving towards open source. At some time, we will see that. However, I want to emphasize that, right now, at least for confidential computing and TDX, we have the TDX module source code and SIM loader as open source. So, and we invite security researchers out there to come and review our code and actually try to hack it and report the vulnerabilities. So we also actually had a few collaborations with CSPs where we, for example, Google and also Microsoft, we invited their security researchers to actually look into our code and also architecture. And this engagement went for like 9 months to 1 year. And they actually have the report available, and it's public. So we have another program at Intel, which is bug bounty program, where we actually invite the other security researchers and hackers from all over the world to come and do their offensive security research on the Intel products. So we, at some level, we have the open source, but well, when we get into the complete open source, that's I don't know, no guarantee.
So I think it's important to distinguish between credibility and trust, right? Open source. So trust is I'm choosing to believe that what a thing says it will do, right? Credibility is the mechanism by which I feel evidenced towards giving that trust, right? And open source is one mechanism of building credibility to bring towards trust, right? But it is not the only mechanism by which we get trust. That being said, I think it's important to talk about how much open source there is here. For those that know me, I worked for 10 years at Red Hat, and so I'm a huge open source guy. most of the projects like, for example, confidential containers are all open source, right? So basically, most of that stuff from the software or from the firmware up is sort of open source. But it actually sort of doesn't matter because all of that stuff actually lives outside of the trusted execution environment anyway. So it's not part of your trusted computing base. So, and if the security barriers hold, right, they can't actually peer in and modify your code in any way. So it actually doesn't really matter, right? So one of the key principles is that, first of all, whatever you put in the trusted execution environment is the thing that's there, right? So the big question then is the stuff below that, right? So we're basically talking about firmware. And firmware is a tricky situation because, as I mentioned again, firmware is sort of deceptively like software, but has a different supply chain. And firmware from there's different types of firmware, and some of the firmware on different platforms are open source, right? Like there's some modules, for example, on Intel TDX that are open source. There are with ARM, I can say, we have trustedfirmware.org. So because we are a CPU designer, we produce reference implementations of the firmware, and those are all open source. The challenge there is that you, as the person who buys the CPU off the shelf, right? You buy that CPU off the shelf, and what's the firmware that comes with it? Well, that firmware actually doesn't come directly from ARM. It comes from whoever actually manufactured that particular bit of firmware. So the question is, what are they going to do with our open source, right? Are they going to continue to make it open source to you, or are they going to do something else? So it's a challenge.
We have another question at the back. Let's take that. So the question is, how does remote attestation deal with replay attacks?
So all the attestation systems actually have a nonce value on all the platforms. So as long as that nonce value is in fact a nonce and is unique, then it can't be replayed.
Is that something that I, as an implementer, have to validate, or is that just part of the framework that automatically related? Because
the
implementation details get lost.
So the question is, just repeating it, is that something that is clear in the implementation, or something I need to worry about as a user of this, basically?
The software for these systems is still pretty young, and the way that I see it playing out is that the actual validation of all the attestation stuff is going to be part of your software deployment system. So essentially, you're going to have some software that gets deployed. There's an attestation that happens, hopefully automatically as part of that. It'll probably deploy a certificate, to that workload for you on your behalf is sort of like a pattern we're going to see repeatedly. And so, in terms of the actual nonce value, it's unlikely that you will have to do that. It'll be something that's just handled by software. The bigger question is what happens, there's a standard for mutually attested TLS, for example, which is where you have TLS where both parties can do an attestation to each other before they secure the channel, right? And that's a pretty complex process with a bunch of things that have to get verified, and there's emerging standards in this area. So it's still young, but hopefully when it's mature, there'll be very minimal involvement from you.
So I want to move on because there's one thing we haven't talked about at all, but I'm just going to say this is one of the reasons you might have a third-party attester, because it's really difficult to do, but it's really important to do right. So you want someone who's an expert in it to do that. So I've got a question for Fatima specifically. We talked very early on about boundaries, and I said I'd come back to it. So we have some very evil people in this room, people who decap with some very nasty chemicals I discovered yesterday, actual chips, and try to do very bad things to it. So presumably chip security is perfect, and so, well, obviously not. What is the scope of protection that we're looking at about in CPUs with TEs? How would you describe that?
Well, actually, there are a few architectural items that we are necessary for the TE to run in case of TDX technology. We actually require MKTME multi-key memory encryption. And also we actually define a new CPU mode, which is C mode. And also we have a TDX module, which is a signed module from Intel that actually manages the private memory and key IDs for the TDs. So without any of those, the TE shouldn't be actually working and shouldn't be actually operating. The C mode, the CPU, the new CPU state is actually necessary for the TDX module to run, and the TDX module doesn't run if it's not in a SIM mode. So those are the features that actually are added to the technology.
And in terms of scope of protection, I don't think if you go to one of these manufacturers and say, is this a FIPS 3, level 3, whatever. This is not what we're talking about. We're not talking fully tamper evident and tamper resistant. These are standard dies on standard chips, right? So if you have long-term physical access with some of the tools that you folks have, or a nation state, these are not the sort of attacks we're trying to mitigate generally. Nathaniel, do you want to say something to that?
Yeah, I do want to add a couple things. First of all, for the actual offensive people in the room, we like you. Please do what you do and come disclose things responsibly, right? That's the key point here is it's not that we don't want you to find those issues, it's that we want to figure out a way to handle those issues in the most responsible way possible. I did want to add, you said not FIPS, but I do think that all of the implementations, if I can remember correctly, from Intel, AMD, and from ARM are all at least targeting to make it possible to be FIPS 140 level 2, not level 3 because that requires countermeasures. But yeah. I think that's the point.
Fahima, do you want to add anything to that?
Well, actually, I just want to say that we have to be realistic and adjust our expectations from a security service that we provide and security product that is out there. So we can't do only so much with a TE. We can't actually eliminate the physical attacks, very low-level hardware attacks, or DOS attacks. What we actually offer with TE is the protection of the code and data in terms of integrity and confidentiality and the state of the CPU. So, different attacks, it depends on the implementation as well, on the application level. So that's
cool. We have, I think, time for maybe one or two questions. Gentleman there. Yeah.
So you talked about protection on CPUs. You also mentioned that it's not low-level protection. The low-level stuff, you say there's no protection for that?
So you say, I don't think we're saying there's no low-level protection.
I think the point is to protect the lowest level and then use that lowest level as a foundation to build additional protections for all the layers above, right? That's why it's important that you have to have a hardware root of trust actually in the CPU to be able to do all these things. And it has to be the very first thing that executes when the CPU is powered on.
What I mean by this is that, for example, I can give you an example. If you have an application that runs a cryptographic algorithm and actually treats 0 and 1 bits differently based on the power of the CPU, then you can measure the power of the CPU regardless you have the TE or not, right? And then differentiate between 1 and 0. What TE provides is the data confidentiality and integrity within that trusted zone. With the aid of root of trust.
And if you're worried about those sorts of things like constant time crypto implementations are very interesting mitigations in these situations. Any other questions? Yeah.
What is the threat model that are really protecting against what's happening? So talk about bit probing that's maybe not really protecting against it. People who have network access.
So that's going to depend on the silicon manufacturer. Fahima, do you feel able to talk about the Intel case specifically or not?
Well, we actually, when we talk about the in-scope attacks, we actually invite everybody to attack different levels of TE. attestation, a private memory access, DMA access, anything that is related to TE. But we do not actually cover DOS attack, for example, or as I said, very base hardware attacks like probing or exhaustive hardware attacks.
Yeah, ARM's a little bit different, again, because we license IP for CPUs. But we are designing IP that is designed to withstand a variety of attacks. The first attack is the host operating system, right? So that's entirely outside of the trusted computing base. I think it's actually easier to think about this as we're doing two things, really, right? We're doing one, which is we're adding a new security boundary, which is that when you create, for example, a virtual machine, that virtual machine's memory pages are encrypted, right? That's a new security boundary that didn't exist before. Then the second thing that we're doing is attestation, right? That's integrated into the entire platform. And the attestation proves the authenticity of that security boundary, right? The memory encryption security boundary, but also all of the other security boundaries that exist on the system, including, hopefully the package of the CPU, as well as, the processes, different permissions levels and so forth. So essentially all the existing boundaries that are already there.
Okay, so I think we're pretty much at time. Just a final word, Fahima, from you first. Any final thoughts you want to say?
No, thank you very much for your time. I know that it's end of the conference, so thank you, everybody, for the nice, good questions, helpful feedback. Thank you.
Nathaniel?
Thank you, everyone, for coming. It's been great to chat with you, and if you have any other questions, I'll be out in the hallway.
Yeah, and I would say if you or your companies are interested in this, confidentialcomputing.io is the Confidential Computing Consortium's website. It's a Linux Foundation project. You don't need to be a member to come along. So if you're interested in coming along and coming to some of the meetings, you're very welcome to do so. Thank you very much indeed to Antrish and everyone involved for inviting us. It's been great, and thanks for the questions and the engagement. Thank you, everyone.